All right, ladies and gentlemen, hello and welcome back once again. It is our new show. You're dialing into our brand new program. This is episode 3 of Now Streaming. That's right, we've got a whole show dedicated to streaming analytics. It is one of the hottest topics out in the industry today, and frankly, there are probably half a dozen companies now or more that are at least seriously talking about delivering streaming analytics solutions. But the company online today, I think, is the pioneer for this whole concept, quite frankly. They were right up in front several years ago. They've been out in front for quite some time now. We're going to be hearing from my good buddy, Damian Black. And yes, of course, this is yours truly, Eric Kavanagh of the Bloor Group. Streaming analytics for IoT, for the Internet of Things. And folks, I joke, what's bigger than big data? The IoT. The Internet of Things really does present a tremendous range of possibilities for how to monitor your businesses in real time, and frankly also how to predict issues like maintenance, for example, or to better understand how those assets are doing all over the planet, all over the globe, all around the country, whatever the case may be. Of course, IoT has a tremendous number of use cases, and doing streaming analytics with IoT is ideal for really understanding in real time what's happening with your operations. So you can kind of do the math and figure out the number of different use cases that come to mind. Any company that has assets, for example, a trucking company, or any kind of retail operation that has stuff moving around, grocery stores that have stuff in transit, any transit-oriented organization is going to have a great need for this stuff. And of course, lots of organizations that just have assets that are far-flung. You can put sensors on everything. In fact, yours truly was on the maiden voyage last year of the Trenitalia, highly instrumented high-speed train that went from Rome to Naples. The very first voyage I was on there. That's a tremendous use case for streaming analytics. And of course, you can gather all this data too to better understand, once again, issues like maintenance, issues like route optimization. You can save time, save money. There are lots of other benefits too. And really, one of the key components, I think, is not having to wait to understand what's happening. So if you can imagine watching streaming analytics as a hurricane makes landfall or as some major event is happening in a major U.S. city, this can be extremely useful for marshaling resources, for dealing with emergencies, for capitalizing on opportunities. There are all sorts of different things you can do with streaming analytics, and that's what we're going to talk about today. So I'll be sharing on Twitter. Check out SQLstream as the hashtag. That's SQLstream. And with that, I'm going to hand it off to Damian Black. Take it away.
Thanks a lot, Eric. Thanks for the great introduction. Thanks, everybody, for being here today. We're just going to kick off, just let you know that the software that's available, unrestricted in terms of functionality. It's freely available for download. It's going to be free forever. It is limited to 1 gigabyte per day. That's the only limitation, but other than that, it's functionally complete. Everything that I'll show you today, you'll be able to do, register, download, and try out the same experiments. We even provide you data so you can actually repeat exactly what I'm showing you today. The company's background, we've been around for a while, profitable since 2015, which is unusual in this space. A lot of intellectual property that's been developed over a 10-year period. We're talking about 2 million lines of code. That's larger than the Hadoop kernel. 8 broad patents granted. Covers everything from edge analytics right through to your data centers, bridging cloud. We're very proud to be able to state that Amazon, AWS, is actually our largest customer. And they have actually licensed a subset of our technology, which is used in part with the streaming engine within Kinesis Analytics. And so we have a very close working relationship with Amazon. We can connect that to add additional value around that on and off premises and whether they're on-premises partner. And we've won a few awards along the way. So the Internet of Everything is what we tend to think of, which means everything that's connected to the Internet or connected to networks that you can process. And that obviously is all of these sensors and devices, but it's also your applications and your services. It may be transactional data, and there's so much information, and it's just growing, and we're already looking at 20 billion connected items. But obviously, there's a chance to be able to bring the data and gain fresh insights if you can do that efficiently enough and easily enough. And what we're really focusing on here within SQLstream is There are lots of open source projects where if you have the right software engineering and skills, enough money and enough time, you can probably solve a problem. Though you may have to run into some latency issues, you will probably run into some cost issues. What we're trying to do is to provide something which is a lot more efficient. You'll need a fraction of the hardware to execute your analytics. It's based around SQL standards that are familiar to everybody, but we also support Java as a first-class alternative to go beyond that. But probably most importantly to a lot of people is it's so easy to use. It's easier to use than a spreadsheet, yet you have the full power of SQL if you want to go beyond that. So we're going to show you some of that today, and the way that we can do that is we automatically, intelligently generate the analytics with human intelligence, the analyst, if you like, guiding the process. So there's a lot of data out there. We need to be able to harness that. Lots of opportunities for your businesses in terms of new revenue, in terms of new insights, in terms of improving the efficiency of your operations, and getting a better experience for all of your users. What we see as the key ingredients within the streaming platform is not only providing this analytic engine and capability that will crunch. In fact, we can process in excess of 1 million records per second per CPU core. You think about that for a second. So I'm actually using a Macintosh here. It's got 4 cores, actually hyper-threaded to 8, and this system is capable of processing well over 8 million records per second. Simple records and simple SQL analytics, but just to give you an idea, I mean, it's pretty mind-boggling. But the data wrangling part is the part that I think is really breakthrough. We built our platform around the data management solution, and we allow them through this intelligent interaction with the data to be able to generate your applications for you, working with you. And I'm going to go straight into a live demo because seeing is believing in this case. So we're going to show you how we're going to generate these real-time suggestions here, intelligent suggestions. You're going to get to see and connect your data in minutes. And we're going to build an application, actually tracking buses, first of all, real-world data. And again, it's available for download in the virtual machine. So let me move now to see that virtual machine. If you, this is what the screen you'll have. You can control the various servers and services. And if you come down here, first thing you can do is you can see there's 2 sources of data, and I'm going to turn both of them on. There's a source that's being broadcast through Kafka and on the topic CDN. And we're also going to be replaying files of bus data, and we're going to write it to this directory and this file. It's /temp/buses.log. And now that just to show that data is now being, if you like, dripped out, so we can process it as if it were real-time data. Now the timestamp that it carries for the bus data goes right back to when we first did the project in 2014, and we'll show you how that's not a problem. We don't have to operate upon real-time data. We can also operate upon past data, in which case we'll go as fast as the data. While there's data to process, we will use our cores to crunch through all of that information. So the first thing to do is to start up a project. I'll get rid of this old project that's running here and delete that. And I'll show you there's some demonstration applications that are built in, and I'll look at one of those at the end. But first of all, I want to just show you how easy it is to build something from scratch. And I'll call this one a secret demo because it's absolutely the opposite of that. And we will power up that. And here we are within StreamLab, which is this data wrangling tool that basically is talking to our virtual machine device, which actually happens to be on this IP address within this machine, on this port. And we're operating through Chrome here, so it's an intuitive browser-based interface. You could be same interface if you're running this on AWS. We are supported on Marketplace. We're supported actually also on Microsoft Azure. We have downloads for VMs. You can install on Linux boxes. You can run this on Docker. You can access this everywhere. So within this system, we want to deal with external connections. And in case I want to use this, I will actually go to a Postgres database, and I'm going to put in the credentials so I can actually log into this system. The username is demo, and the password is a highly secure demo. And I can just execute that, and I should now have a connection credential. One external connection. So this is where you put in for if you want to write data to a database, or you want to enrich your data streams against the database, then it needs to have the actual connection with the password, credentials, etc. We go to our sources to connect to data. So let's look at some external streams. I want to show you just how easy it is to connect to, for example, the Kafka data we showed earlier. So we could actually pick now from this a menu of sources where we want to connect to. If you want to connect to Kinesis data, you can just put in which region you want to connect it to. There are other parameters, often by the default you don't need to change, and then put in the stream name and off you'll go. For Kafka, all we have to do here is just go to this CDN topic, and now I'm going to show you one of the first magic elements of this approach. It will discover the formats of the data for you. I just have to click in Discover Format, and I can tell it how long I wanted to have a look at the data and how much you wanted to sample before it. 50,000 bytes. And so we'll now start that, and it'll have a look at the data, and it'll scrutinize it, and we'll try and find out what format the data is in. And it's found out that, in fact, it's in JSON format. I'll accept that. So it's already now discovered for me a JSON. It also supports comma-separated XML, some binary formats. So whatever data for many formats you'll be able to do and immediately connect to the information. And in fact, it looks at the ranges of values and will come up with suitable data types to hold that in. And if I wanted to see that it really is there, I can just ask for 5 rows, and it'll sample 5 rows. And we can see now that the records are here, and it looks pretty sensible. So we'll come back to this later, the CDN data. Interesting here is the row time, which is Greenwich Mean Time. This is the timestamp right now, so it should be on August 24th. And of course, if it was just a Kafka topic, you'll just have the payload or a log line, the payload. But because we've discovered these other fields, we've already created this for you. So that's already done. Now that could be a couple of weeks' work, at least, just to connect to data, parse it, and get it sensible. We've done that in just a few seconds. And we have a streaming source. And I'm going to create another one now, and I'm going to look at the bus data. So we come back into the same screen. We saw Kafka, AMQP, similar. We support both of the protocols here. Sockets and WebSockets, TCP/IP, the familiar WebSockets protocol. There's a lot of live feeds that you may want to talk to, HTTP as well. And we're talking about files now. So when you have your data in files, in this case, remember it's being written to this directory. You can put a pattern in here, and it will follow those log rotations. And again, we hit this Discover Format. We'll use the previous parameters that were good before. And very quickly, it discovers it's in JSON format. And in here, we have the fields. And here we have the insert types, and it's even got the JSON parse if you want to look at that. Now, this is data on buses in New South Wales. And buses tend to not go faster than 256 kilometers an hour, normally, unless they're driven off a cliff or something. So it's decided to put this into a tiny, and it's an 8-bit integer. But I can override that and say, look, please place this into a floating point number, 64-bit double. I just override that type, and it's good. I can sample 5 rows again as before, and I can see that I have some information here. It's looking useful. So let's go up now. And we have 2 data streaming data sources and an external connection. Let's go and start doing some analysis. So what we guide you through this process with an intelligent engine. This is our second data feed, the buses, and let's have a look at it. So immediately now we get to see the data that are flowing through. So again, this could have been weeks of work to connect and parse and what have you the data. Let's look at 25 rows at a time. And have this spreadsheet style interface, we're looking at the data. Now we're capable of processing millions of records per second. So what it will do is it will actually show you a subset of the records so as not to overwhelm the user, the interface. You can also turn it into a throttling mode where you set the rate that it's going to present the data to you, in which case it will give some back pressure signals to stop the generation of the data if that can be controlled through something like Kafka, to slow it down so it won't overwhelm you. You have either option to go with here. So now we're looking at this live data that's going through. We're seeing some timestamps here. This is the reported at time. Now I said earlier this is from 2014, so if you look at this, these are timestamps. They're actually in string format, they're in character format, it's not in a timestamp format. But the system is intelligent, and it's already given me a suggestion here to convert that, parse it into a timestamp. If I hover over it, it's giving me metadata information such as the maximum and minimum values, whether it might be a longitude or latitude, whether it could be a partition key. And in fact, the scrutinization rules that are built into it can be extended. So if you want to put in custom scrutinization rules that are looking for certain formats of data, you can extend that and have that automatically detect them. Now, why do we do that? We do that because the scrutinization rules, the metadata that's inferred, is used to fire into this suggestions engine to come up with useful suggestions. The other thing is the human being, the analyst, the user, could be a developer, can also tell it to focus in certain areas. So you have palettes and sub-palettes of operations, in which case it will just target those suggestions in the area that you care about. I want to filter data, for example. So let me show this in action. So how do we actually fire off and use one of these suggestions? We just click on this plus. And behind each of these suggestions in English, which just says here, convert the reported at field to a timestamp using this parsing format, is a template. The template is into SQL and maybe embedded Java. You can actually extend the engine to put your own templates in. So if you've got some developers that are SQL whizzes, or there are certain kinds of analyses that you've proven with your SQL and Java code, you can have those as templates that get instantiated. And you just click on that, it basically instantiates the template, it's generated the analytics for you, it then optimizes them, executes them, and immediately in that sub-second you're seeing the results back in front of you. So you'll see now, this has changed to yellow, it's a timestamp type anymore, it's been converted as a real timestamp. If I want to undo, I don't like the path I'm going down at any point in time, I can just hit minus, and I'm back to where I was. And I can take another path. In fact, I see here a more useful suggestion. This is not only make that conversion, but replace this real-time row time with the originating time. Now, very often if you're processing data such as sensor data, it may be just a few milliseconds ahead of the time that we're processing here earlier. But because we're replaying old data, it's actually years. But we don't care whether it's milliseconds or years, because when we do all of our processing, we respect those timestamps. The analysis we do is going to be relative to those timestamps. So what we have all done now is time travel back into 2014. Now, if I looked at this data, here we go, I'll stop now. I see here some bad data just by eyeballing it. There's a bad sensor. There's a latitude and longitude of 0. Now, I happen to know this is in Australia, and when I last looked, Australia was not at latitude 0. It's not on the equator. So that means that I've got a bad sensor. No problems here. I can just get some suggestions around filtering. In fact, I get parameters that I can get hints on, and I can, for example, reject the rows where the latitude is equal to 0. And as I hit 0, it's generated me a suggestion which corresponds directly to that. I can read that as
yeah, those suggestions are coming in dynamically, right, that you're reading from that left-hand column?
Absolutely. It's all changing in real time based on where I tell it to focus and the patterns that it sees in the data that are coming in. So we've now basically rejected the data, and we're seeing now that hopefully we're only going to see good longitudes and latitudes. I can let's go and do a basic analytic operation now. So let's go and let's compute the average speed of the buses. So we'll give these parameters to the suggestions engine, and it says over a sliding 1-minute window, take the average of speed, and we're going to create a new stream from an old stream. That's the way this works. We don't side effect the incoming data streams. The data model is a bit like a database table, but infinite, where records are always being added to the end. So that is, we're going to create a new column called A speed for average speed, and I can click plus, and I can, for example, put in here, let's pick the last value as well. It's the last value we got for the speed, and I'll call that L speed. And if I did this now, I've got a suggestion already here. I can just broaden this to make it a bit more visible. Over a sliding 1-minute window, perform the aggregations, compute the average of speed to create a column called A speed, compute the last value of speed to create L speed. So that's going to do it across all buses, and that may be useful for me. But I can also use this partition to do it on a per bus basis. I can partition by the sensor or bus ID, in which case now it's going to do this on a per bus basis, and it's already immediately updated the suggestion. And I click on that, and we're going to be computing now these new columns. So this is the average speed and the last speed. And as soon as I've done that, I realize now that I'm seeing all of these zeros that what I wanted to do, in fact, is actually put a filter stop before that. So I'll just undo that operation, and I'll go back, and it will remember this so it'll be very fast to do this. I'm going to go and filter out the buses that are still gaining speed. So I want to only accept, for example, let's show accept the rows where the bus speed is greater than 15 kilometers per hour. And that means that buses are stopping to pick up passengers or slowing down and accelerating. We'll get rid of that and we'll just try and deal with the more steady state of the buses. And I want to go back to my analytics and let's go back to this suggestion here, and it still remembers it, so I can now layer that back on top. And so now when I compute my average speed and last speed, we're not going to be dealing with a zero case anymore. So this is looking at what is the true average speed that's happening. Now, as I think about this, I also realize that 1 minute is not really a good interval. I can change this here, and I can dump this into the template and make that 5 minutes immediately, and it will recalculate that now over a 5-minute window. If I want to go now, I want to try and, I'm going to categorize the speeds of these buses. So what I will do is the way I do that, I override that. So what I will do is I'll take this average speed, and I'm going to create a copy of that field, duplicate that field. That's a basic operation. And so I'm going to get a copy now of the speed, and I'm going to use that copy to actually classify it. So I'll click on that column, I'll go to Analytics, I'll go to Categorize, and I'm going to make the default category for a bus to be normal. It's in its normal operating speed, but I'm going to make it as a speeder when the speed is greater than, and I look at the ranges here, I can even hover over it to get the maximum value. I can see there's a maximum of 103 and 16. If I look at the values that are flowing by, 65 seems to be already a pretty fast bus. And I want to find the slow coaches, let's call it slow, but if they're going less than 25. And I've got my suggestion already generated. And so I now I'm classifying these into normal speeders, and I'd like to see slow to get the full. These are slow. Hover over that. It sees that there are 3 unique values. So I've now classified this. I'm going to use this for some charting and graphing. I wanted to show you one other operation, just how easy it is to use that database connection that we had before. Actually, it's not there for some reason. Let me go and see. Got a problem with that connection. Maybe I don't have the database. Oh, I know. I haven't created my external table. Okay, I'm doing everything live. It's real. What I didn't do is actually take that external table and add that as a source. I want to enrich that. So to do that, I'll take the database connection here that we did before. I'm going to access the drivers table and discover the columns. And it finds these columns. I can similarly sample 5 rows. So this is this is something which maps the bus ID to the driver, what lady or man's name. It's all fictitious data. So that's working. I can go up, go up. I go back into my guide now. It re-executes this, the analytics. I can now go and you see I've got this connection, and I can join the driver number against the ID. Now I could cache the data, I can prefetch the data. I don't need to do any of this right now, but to avoid those round trips that you're going from your server to the database. And I should just be able to then join in the other attributes with the driver. And so now we have the names of the driver as well, just to show how easy it is to combine the data in that way. Now, if you want to see what is happening to the data as we've gone through, what we did, we started off the original stream, and it's still there. There it is. Different columns, different capabilities, different values. And we've gone through a series of these transformations. That all of these queries are running together in a massively parallel environment, very, very fast, and optimized with our SQL optimization technology. But I can look at any of these points in the pipeline to see what were the fields that were operating at that point in time, and what were the values. And it's thrown up an instant dashboard so I can look at my data. But what I'm going to do now is something a bit more sophisticated. I'm going to do a map and table. We're going to use a more sophisticated built-in dashboarding capability, and we're going to first of all, give it some hints and suggestions for what I want to use for the longitude and latitude. For the value, I want to use, let's take the average speed, and for the key, we'll take this classified version. So we'll color code it based on whether it's normal. I'm also going to change it to 25 rows so it looks better. And it's going to be all around the bus ID. So we have these parameters, and again, it's generated a suggestion here. Click on that. And we've now got a dashboard. Before I go into the dashboard, I want to show you what we haven't had to do. What we haven't had to do is
your audio is getting strange. Your audio just got strange. Is that the cell phone?
I wonder why.
That's better.
Okay. Let's try again. So I apologize for that. What we didn't have to do is to understand SQL and write all of this SQL code. And each one of these SQL statements, by the way, corresponds to about 10 pages in something like Google's data flow streaming or in Kafka's streams. A lot of code you'd have to write. This is all generated for you through the suggestions that we've done. It's all optimized, and it's going to run somewhere between 10 and 100 times faster than those alternative technologies. So we didn't have to do any of that, but if you wanted to export that and work with SQL developers, they can do that. But we're going to go and click on this eyeball and just immediately start looking at the data. So here we are. We're getting records in Australia. I'm going to change the panel display. Now here, we saw, this is the instant views of records coming up at any point in the pipeline. We saw this instant tabular view of data. We have numbers of options for looking at the latest rows. I also here, we can look at rows over time, graphs and charts and other nice things. What we want to do is look at that one, double chart, geographical and 3D. So we'll look at the pan and zoom map. We'll select that. I will try to center this. We will zoom in a bit. There we go. Zoom in a bit more. Now, I can do is set up some parameters here. I want to show up to 1,000 events. I'll do that, 1,000 at any point in the display. And I'm going to change some preferences so that I will uncluster the events. I will take the diameter of the circle, divide this average speed by 5, and I'll add on 2 so actually the circle doesn't disappear. I'm going to show the most recent event and the trail. I'm going to pop up the actual average speed value, and didn't see speeder here on the values went through, so I'll put speeder, normal, and slow. Speeders we will show in red. Normal will be in green. And slow in yellow, shall we? Review all of these parameters, see if it all looks makes sense, update it. And now we're actually seeing, we're getting an insight into the data already. We can zoom in and start to see now, if I click on this bus, doing speed of, last speed was 79, this average speed of 79, got an average speed of 56, and here we have a speed of 70 slow bus. We're seeing the data that's flowing through here. If I want to actually save the dashboard, I can just hit save. And then just to show you, we've already built this application. I can get the URL from here. I can go to another tab. I can paste it. And we've deployed our application. So we've actually gone through raw data. We've discovered the format. We've filtered the data. We've done some drive analytics. I could write this out now to another stream. I could actually, from the output format, I could go back and I could convert. I could write, once I've got it into its internal tabular representation, it's tuple-based flows here, I could write it into XML or comma separated. In fact, through the underlying server, you have access to all of the wealth of the capabilities that's supported within the server. That means enriching against a large number of data types. You could write it in Avro format, many of your popular Hadoop formats. And you don't have to be a data scientist or a programmer to use this. It's that easy and intuitive to use. Very, very simple. At any point in time, by the way, you may have wondered what this route to sync was. If I wanted to keep my streams, I can just publish the stream within the streaming server, give it a new name, Damian Stream, and then anybody else can then pick up and then work with that stream and derive their own visualizations, enhance, enrich it, filter it, maybe join it with another data source. You can join streams together, streams to one another, streams to tables. You can even join a stream with itself. So you saw that we could also select from rich variety of data. It gives you an idea of the power of the platform. The kind of thing, this application, very similar to this, before we had the power of the data wrangling, but we still had the productivity of a high-level language SQL, took 2 engineers, 3 months, and a $250,000 project to provide a bus speed monitoring project for New South Wales, the government of New South Wales. Now, as you saw, we can build that same application in about 30 minutes, and I built a reasonable subset in about 5 minutes. So that gives you an idea of the richness and the power of the platform. Eric, any questions or?
Yeah, we do have got a couple good questions here. Let me throw one over to you. One of the attendees is asking, in order to provide integrity-based analytics, how does the software know it has a quorum to report? In other words, if there's a sense giving bad data earlier, what if 4 from 10 sensors were not working correctly? That you can set up some kind of rule to identify that, but otherwise, what's your advice for knowing that what you're looking at is accurate?
Right. Well, that's a very good question. Now, you can never know that it's completely accurate because you have to see every record, and from the beginning of time and going forward into the future to know whether there's ever going to be a problem with any of the data. So you have to decide when it's good enough right now. But you can capture the data, and then you can write rules or have separate pipelines to, for example, we can have suggestions that will break down a field and parse it or classify it in a different way. You could have different derived views of an originating stream. You could start off with just a raw payload, and you could derive all of this parsing yourself through a series of steps. And then you can write different pipelines to deal with different situations of bad data. And if you get an error, there's an error stream that's created, and you can go back and also do exception logic to process those. Now, in the real world, you're always dealing with different forms of data. You want to have the mainline pass dealing with the most common expected case, and then you'll deal with different scenarios with different exception logic. And you can decide whether you want to reprocess, whether you want to highlight those in a separate dashboard, write them to a database or file, or whatever you want to do. But you have the full power to do everything that you need to do here. And of course, the beautiful thing is you can get some insights immediately from the metadata as to what the maximum minimum values are, the types, whether it's, for example, a partition key, whether it's something that could be used to identify uniquely other correlated columns within the data.
Yeah, and you can consume traditional data sources as well, right, and essentially treat them as streaming. I'm asking because we're getting a couple questions here like, can you take data from MySQL? Can you take data from traditional legacy non-SQL data sources? You can grab any kind of data and treat it as if it's streaming, right? Yeah,
we can read data from message queues, from files. We'll read them line by line. Each line will be a message. If you aren't doing automatic data discovery, you'll have 2 columns. You'll have the time that the server receives that record or is accessing that data. And so every time it reads another line from the file, that will be the timestamp that it writes that into the internal stream. And then the payload will be the column. And then you can go through and decide, I want to, for example, perform a regular expression analysis to pull out a certain substring. Obviously, you could have different, we have different support for things like syslog and other commonly recurring formats. So unlike a Splunk type system where it's having to guess the formats and then store that, and that can lead to garbage being detected and stored forever. So you have garbage in, garbage out forever. In our system, we will convert it into these streams, and you only store value when you want to store it, but you can still analyze it on the fly. And it's not just, you don't have to use discovery. You can use human intelligence to help sort through the data and see that it's good. Other sources, databases, we can read tables and turn them into streams, basically going through row by row. So yeah, you can process pretty well any data through this mechanism. what we did here was replay old files and drip them. The reason we did that, you may wonder, why did he do that? Well, part of it's force of habit, but the other thing is if I forgot to turn on throttling, I would literally be processing 1 million records per second, and it doesn't make for a very exciting demo. I'll click it and turn it, and the data will be finished. I don't have enough data here to make that meaningful. So instead, what I'm doing is I'm dripping it out at a rate to make the demo last. Okay, hopefully that makes some sense, Eric.
Yep, no, it does.
So binary and ASCII, text files, doesn't matter.
Okay. And in terms of SQL, I mean, this is ANSI SQL compliant, right? Can you kind of talk about the importance of having an ANSI SQL compliant engine as opposed to something that is SQL-like?
Yeah, this is right up to the 2011 standard. Has some elements of 2016 in there as well, which is important. I mean, we test, there are a number of reasons why it's important. If you have proprietary data formats or even things that are SQL-like, you can actually change the meaning from release to release. And the meaning of the data may be critical to your insights and your application. You want to be sure that the analytics and the data are going to be consistent from release to release. And the best way of having that is having a standards body. Because even if you've got your own well-used proprietary product, I have a friend who built a company around sentiment analysis. He used a popular NoSQL database system. I won't go into what it is, but they changed the semantics of some of the queries from release to release, and it completely broke his applications, and he almost went bankrupt because of threatened lawsuits by some of his customers because he was not aware of that. So the benefit of having a standards body behind you is that you have to then adhere to those standards. It provides that sort of baseline to work with, and it would obviously have been easier for us to just invent our own wonderful language, but the power of this is to unlock the value that a lot of companies and people have made in existing SQL analytics and in skill sets. The way you talk to this system is through JDBC. We have the world's fastest JDBC driver in terms of throughput. The performance comes because the execution is embedded within a Java virtual machine. C++, highly optimized. It runs lock-free. We generate the schemas on the fly so we don't have any overhead for data types. And it's very compact. If there are null values, there's nothing being stored at all, and that's where we get the blinding performance. It's about 600% faster than the nearest alternative product we've seen so far. And that happens to be also a proprietary product, not open source. And that proprietary product is about an order of magnitude faster than most other systems. So this has the potential really to scream. That's really important in terms of efficiency. Again, a subset of this system was licensed by Amazon for Kinesis Analytics. For them, it's really important, obviously, to not have to deploy 100 servers when they can deploy one. And we think it's important for all customers. And some customers actually, some developers would rather deploy 500 servers because it looks good on their resume. But most customers would rather, if they can actually process more data with just a couple of servers, it's the better option. It's much less expensive, and there are fewer parts to fail. And if you're running on the cloud, you're going to have a much smaller bill as well. So that's where we've come from. And then we've been working very hard on this productivity to make this so that anybody can build these applications. And as I said, the templates are customizable. It actually just takes developers to do that. We can work with you on that. Same thing for the scrutinization rules. The dashboarding technology is also based on open source D3 and Vega components, and we are opening that up as well. So if you want to be able to extend that and create your own dashboards, that's fine. We provide a microservices interface also, so that you can actually build your own dashboards and connect to it very easily. You also, I said, you have JDBC. You can start and stop queries, create streams, read and write records. Everything you can do through Java. You can build your own Java operators and load them in, and you can build your own input-output adapters, and we provide a rich library of those. And of course, you can combine SQL written by SQL developers and Java written by Java developers, all operating with the server alongside someone that's using StreamLab and not wanting to work at the SQL level at all. Because once they publish them as streams, they can be consumed by your Java developer, by your SQL developer, or by another StreamLab user. So it gives you the most kinds of options.
Here we've got a question about cloud, too, deploying in the cloud. Do you want to talk about Amazon Kinesis and what role you're playing there?
Yeah, so it's again, Amazon Kinesis, you see it's based on SQL executing, and they licensed, if you can look at them, there's a press release on this, they licensed a subset of our SQL engine in order to provide that. Now they've done lots of their own added value with regard to plumbing it into the Amazon cloud and accounting and other systems. But we have, we've all co-developed with them a Kinesis adapter, as you saw earlier, so you can actually talk to those Kinesis streams and add value off the cloud on premises, or you can build your own applications with using, for example, StreamLab and our dashboarding capabilities, reading from those Kinesis streams and then publishing back maybe the results back into a Kinesis stream to continue with Kinesis. So we work very nicely there. We also allow you to be able to federate and connect servers together, so you could have servers that are, I have some more slides to show you this. You could have servers that are operating different clouds or on premises. You could be filtering and processing data on your factory floor or out in the field if you've got agents using cell phones or other devices. I mean, you can process all the data in the most appropriate place. And then when you connect these servers together, it's as if those streams are local. They can see the structure of the data. As I said earlier, they will work and synchronize around those timestamps. And that will take care of any delays or jitter on the network. It's all asynchronous, so when the records are available, when all of the inputs are available for any operation, it will fire and it will generate an output. And it will generate consistently the same information in the same order. So it's very flexible, extensible architecture for you to be able to connect to your Internet of Things devices wherever they happen to be. And our ultimate vision is to have this millions of these servers completely transparent to you and automatically optimized over that cloud, and maybe even built into the networks instead. So instead of one day Cisco's routing you these dumb packets where you have to pull them all together into a single server to add value, the actual network will become the computer. It would be transforming the stuff as you go. That's the sort of the ultimate vision. That's what we've been patenting. We're heading toward that. Obviously, it's a lot of work to achieve that vision, and we're on our way.
Yeah, that's amazing. And you talked about 1 million rows per second per CPU core. That's how much you can ingest. And you guys did some work on customizing the JDBC driver, right? Can you talk about that for a second?
Yeah, so it's not just ingesting. That's the analytics. I mean, obviously, depending on what you're doing, that's the analytic operations throughput. It's in excess of 1 million records per second per CPU core. And that's one of the things you can do is measure the performance on your particular system. On a VM, even on this laptop, it's in excess of 1 million records per second. That's small records, say 16 byte. I don't know. Maybe probably sub 64 byte type records. Obviously, as the data gets larger and more complex, the number of records per second is going to go down. And that's talking about, for example, doing something like a SQL aggregation. If you add more SQL operations, your performance will go down as well. And it depends on if it's able to parallelize it across all of the cores and so on. But because it's running lock-free, that means normally one of the hard things to do is to build applications that can take advantage of these inexpensive cores. And the way you have to do that is you have to be sure that any part of the application that's running, because you have multiple applications running at the same time, they must not be touching and changing the same data in memory at the same time. If you do that, you're going to get basically random corruption. You're never going to know which one's going to touch it first. So what you do is you lock the data. So only one processor can actually access it at any point in time. If you get that wrong, you can get deadlock. They're all locking different pieces, and they can't complete. Each of them can't access all of the information that they need to move forward. So there are all kinds of problems with that. But obviously, if you're locking the data, it's going to be slowing things down because other processes are going to be waiting. We run lock-free. Think about that. So what that means is we write the data in such a way that we are sure you cannot get this corruption, that any of these processes are able to process it at the same time as soon as it becomes available. So they're running blindingly fast, and that makes a huge difference to performance. We even have lock-free I/O. And around that protocol stack where we multiplex, we combine multiple streams together into single channels, communication channels, that protocol is built into our own JDBC driver. So it's a homegrown, from scratch JDBC driver. In fact, all of our Java is very carefully written so that we do not allocate Java objects. We pre-allocate all of the items we're going to use, and we recycle them. Because the problem with Java is something called garbage collection. You have to scavenge the memory when you run out of space and then compact it all down again, and then off you go again. Now that leads to pauses in delay and latency and slows down performance. What we're doing is automatically recycling all of those objects. We don't use Java strings. That gives you, our Java is still much slower than our SQL, but it gives you the fastest possible that can be done with Java. And those techniques are employed within our JDBC driver, which is how we get that high performance and throughput as well.
Yeah, that's great. We've got an attendee asking, Ken, I think you kind of talked about this, but maybe just answer the question he's asking specifically. Can you pull syslog firewall and SNMP trap data as well? I guess he's watching out for hacking and other kinds of unpleasant activities in the network.
Yeah, absolutely. I mean, it's very straightforward. And the good thing about this platform, even though it's not open source, we're happy to open source any adapters to people if they want to work with them. And we have a high-level API which allows you to be able to instantiate and create new agents or adapters. Now, agents run in pure Java. They run on other servers. So, for example, in a data center, you may have on every web server, you may install an agent that's reading through those syslogs. As people use the web, those log items are written, and that will convert them into streams that are passed back into one server you may have that actually is doing an analysis of all of your web servers. So agents will operate remotely. You can also instantiate that as an adapter which plugs into the server, so it could then pull the data from all of those other servers. If you didn't want to install anything on another server, it could be accessing those files remotely. And yes, we can support syslog, but even if we didn't, and there's any other data types that you want, you can very quickly do that. It's based on Java. There are lots of open source libraries for connecting to everything, and it's very easy then to wrap that into a new data source. And even if you didn't want to create an agent or adapter, and for some reason you didn't want to do that either, remember, you can write a Java program that will be reading your data source, and then just write JDBC records into the server, and then it suddenly becomes a stream which you can process with the server. So there are very many options for how you may want to build this system. And you don't have to worry about SQLstream building all of these things for you. Now, we actually have a rich library of about 80-odd adapters, often with optimized interfaces to systems like Oracle and Teradata and SQL Server and most of the databases and Hadoop systems that you all care about.
Okay, here's another very good question. Yeah, it's a good question for IoT stuff. One of the attendees is asking, do you need microprocessor-type sensors for edge analytics as opposed to dumb ones? What about the actual devices that, what kind of processors they use?
Well, that's a good point. So on the edge, if you want to run the full power of an S server that's doing all the SQL analytics, the smallest that we need to skinny down to would be an Intel Atom 2-core, 3 gigabytes of memory. But in reality, you're going to need more than that for your working memory. So probably 4 gigabytes of memory and Intel Atom 2-core. Now, that actually sounds like, for some people that may sound a lot, but actually it's a very inexpensive device. And we're running on, for example, Contron's Internet of Things gateway, world's second biggest embedded system supplier. They are working in, you mentioned the train example, they work with locomotives with embedded technology there. We also have agents, which are pure Java, which are much lighter weight that can run. And if you ever needed to go below that, we have a C++ protocol stack, which you could then embed to make something arbitrarily small, but you'd have to do some programming to be able to talk to one of our servers. And, you know, agents talk to servers. They do things like parsing and filtering as well. And the servers, again, can be skinnied right down to these small devices, and then they can be federated to bigger servers and so on. So you can build whatever hierarchy of processing that makes sense for your budget and for your processing needs.
Okay, good.
It runs on Linux. Here, the server runs on most leading flavors of Linux, but it does run only on Linux right now. So we provide virtual machines and so on. Remember, the technology here, if I go past the architecture of the federation, the other thing, of course, is this is a data management platform. So you may have lots of exploding variety of data that's come from the internet world to the mobile to the Internet of Things, we allow you to be able to combine these in different ways so much simpler. It removes all of that, cross-product transformation complexity, and we'll discover it and read it in any format, and we'll write it to any additional format. So each application will get the data in the format that it's able to consume. And then finally, if you look at, this is another way of looking at the space here of what traditional analytics have done and what we can do here. If you go from operational intelligence to security intelligence and Internet of Things, we have a large space where we can add value. Now what we're doing is we're not here to replace historical analytics. What we're doing is we're querying into the incoming streams continuously and updating the efficient. And when we find something suspicious or of interest, you'll then trigger off a directed, targeted historical query to combine and finish your analytics. So if you're looking at, for example, a security breach, you'll be looking for certain suspicious patterns continuously in real time. When you get your miscreant suspect, you then may want to find out what systems have they touched, where have they been. Lots of applications covering fraud, security, advertising, promotions, cross-selling help, pricing, real-time discounting, billing, rating, failure and fault detection, service level, quality monitoring, prevention and protection of incidents and crimes. And again, the good news is if you want to play with this fully functional, up to a gigabyte per day, it then throttles you back, so it doesn't stop working, it just keeps you at that rate of a gigabyte per day. You can do this, it's free forever, fully functional, you can build it for test applications, you can deploy if you want to. Again, it's only going to process a gigabyte per day on a given server. You can put multiple servers out if you want to go to more than that. So
we got a couple, got a couple last questions here.
Download it. So today, you can download. Yep. Okay.
So a couple last questions, and then we'll have to stop right at the top of the hour. But how do you scale this? You just add servers, right? If you need to add additional scale, you just add more nodes, right?
The first thing you'll do is turn on more CPU cores. Then you can add more servers. You can also add, you can distribute those, or you can partition them using Kafka. You could also use Kinesis or other systems, but we're most familiar with Kafka to partition the data across those servers very efficiently and effectively. So each server will process a partition or shard of the data that's going through. And then you can also pipeline the data, the processing across these servers. So you may do some of the processing of the first part of the pipeline on one server, the next part of the pipeline on another server, and then finish maybe the pipeline on a third server. And as the data is being finished on the third server, more data is coming in on the first. That's how pipelining works. It's a different way of parallelizing. The same thing that's done in manufacturing, say on automobiles in your factory floor. So lots of ways depending on what you want and what you want to achieve. Again, it's going to be probably, I mean, it sounds ridiculous. So often I'll be able to say 10 times faster, but in many cases it will be much more than 10 times. It could be 100 times plus faster than alternatives. We have one customer that was using 180 Hadoop servers, 3 hours to process hundreds of billions of records per day to get insights. So 180 Hadoop servers, we provide real-time insights with just 12 of our S servers.
Wow. Yeah, that's amazing stuff.
The raw brute performance. Now, they actually are retaining the use of their Hadoop because they want to use Hadoop to store the data as well. They want to have an historical, non-repudiatable record of all of the records that have gone past. But for the real-time insights, they don't want to wait 3 hours to get those insights with those 180 Hadoop servers. So they instead have turned to just using us with just 12 servers. So if you think about that, that is, and that's a real world, that's analysts, they actually wrote those themselves in SQL. And because they have, peak rate is about 7 million records per second, and those records are about 3 kilobytes unpacked. So we're not talking about toy records. So again, and that's real analytics. Yeah.
That's amazing. All right, one last question for you. An attendee is asking, but for dumb sensors with no CPUs or RAM, what's the intermediary called? He said you mentioned that, but he didn't catch the term.
So often those things will be talking MQTT, and we'll support that. We have a support for ActiveMQ, which will read those MQTT, and they'll basically will read those MQTT. They'll come through as an AMQP stream, which we then process, and you can discover the data and process highly scalable. You can write your own agent as well. If you've got some proprietary format that you want to talk to it, whether it's an RS-232 line that you might find in some old traffic devices. It doesn't really matter what it is. You can easily talk to it. The simplest bridge is then to talk to Java to publish that as JDBC, and then immediately it can be read by a stream. Or you can write a Java program as an agent to read it. The harder route would be to talk to us to basically get a copy of our C++ protocol stack, and then you basically have to build those packets and communicate through that API. But generally, it'll be just a matter of using some configuring software off the box. Turn to us for help. We'll provide free help to get you working and get your apps going.
Okay, one last question. I keep lying here. We're getting good questions coming in, and I do have to jump at the top of the hour myself. But the question is, how do we size the server for processing real-time firewall traffic? Is there a correlation engine to correlate events? Can you talk about that?
Obviously, we can give rules of thumb. I mean, but it really depends very much on what the analytics you're doing. I mean, how many pipelines you're running, the complexity of the format and the data. But again, the stuff is free. You can play with it, and it will help you with sizing, and you'll get an idea. But all I can tell you is it's going to be at least 1/10 of the hardware, and probably 1% of the hardware of most alternative solutions, and certainly open source solutions. And I didn't mention latency. Our average latency is now, it's well below 5 milliseconds. In many cases, it's below a single millisecond. So this is unlike the Spark or something like that, where you're dealing with tens of seconds of latency. We're talking about sub-millisecond latency, and that's really important for certain broad applications, anything that's in the click loop for a user interaction or controlling machinery. So, but the only real way is to, we'll talk to you, give you an idea of what we think is going to happen, but in many, many cases, we monitor, for example, all of California 911 calls in real time. We discovered the San Bernardino terrorist attack. That was all run on a single commodity server.
Wow.
And it might even be a core commodity server. I hate to say that, but that just gives you an idea. And it's processing hundreds of analytics continuously in parallel for 400 call centers coming in. Even before those calls are answered, you've got insights in terms of the clustering of those calls over time, where they're happening, which networks they're on, what's happening to the response time, what's happening to the queue length, all of that kind of stuff that you actually see, and it's powering a very dense dashboard of 4K dashboard. And again, that's all run on a single commodity server. So you'd be amazed what you can do. People forget how powerful computers are because the layers of software abstraction that have been piled on have sort of dumbed them down. But underlying that, you actually have a huge amount of performance. And some people said, well, you know, do we support what do they call, the graphical processors? We haven't had to do that, right, because we actually far outstrip the performance that most systems need today. Now, we can be looking at that going forward. For certain vectorization operations, that would make sense, but you can still interface them today through our extensions into Java, and so if you have a problem that can be mapped onto vector manipulation like that, then yes, you can integrate and it will play nicely with our system, and you'll be surprised. If you use that correctly as a code processor, you may be able to solve all of your problems on maybe even a single server.
Wow. Well, folks, we burned through an hour today with our live demo. This is our new show, Now Streaming. Watch for another episode soon. Big thanks to Damian Black and his team at SQLstream. I love watching this stuff in action. That's what this series is all about, watching applications built, demonstrating the power of streaming analytics. It's good stuff. We're going to see a lot more of this coming in the next couple of years, I guarantee that. So with that, we're going to bid you farewell, folks. We will archive this for later viewing, and we'll talk to you next time. Take care. Thanks for joining the show. Bye-bye.
Thanks, everybody.